Hey y'all, Lisa Marriott here. We're going to be talking about toxicology and dose response curves today because that's the basis for pretty much all of our environmental health effects that we're going to be talking about. So what I want to cover pretty much is stemming from compound interest, which you know I love because it talks about all of the things that are related to chemistry and how chemistry is so cool. And the reason chemistry is so cool is that the basis for everything that we're going to be talking about has to do with these neurotransmitters, the things in our body that communicate. That's the chemistry in our brains, in our bodies, those receptors that make a huge difference for how some of these drugs, the toxicants, and everything else work in our body. So this is from compound interest. It shows generally the structures of these neurotransmitters. And the reason, I'm not expecting anyone to necessarily know the structures, but the reason that it's important is that you're hopefully going to notice some similarities between some of these things. And the reason that those similarities are important is because it affects the way that they bind to receptors. And when you have these receptors, that means that other things can also bind. All right, and we're going to go through that. So what normally happens is that when you have a neurotransmitter, that's humor me here, and that's that natural chemical, it's going to bind to a receptor. And it's not necessarily a one-to-one relationship. You have, say, for example, with acetylcholine, it will bind to either the nicotinic receptor or the muscarinic receptor. And they're shown down below. And you'll also see you'll have nicotine. That probably sounds familiar because, of course, it's in cigarettes, smoking. It binds to these receptors, and those are called agonists. And when we look a little bit closer, agonists is just a fancy word for things that are binding to the receptor, typically in the same spot, and it's activating generally the same pathway to some extent. Antagonists, all that's saying is it's blocking the receptor. It might be laying right on top, it might be affecting downstream, but generally speaking, it's blocking the effect of something working. So for example, if you're talking about various neurotransmitters, we were looking at acetylcholine earlier, you have your different receptors. You have things that are going to bind to that receptor in that same way, or things that are going to block it. So curare, those are your poison darts way back in the day. Those would stop you from breathing, and that's how you died. Atropine, we're going to be talking about in a little bit. But generally speaking, you'll see that you have these pathways, and the cool part is that you'll be able to estimate or generally predict what's going to be happening based on the neurotransmitter system. And that's what I've always loved about it. So for example, if you're looking at dopamine, that is your feelings of pleasure. So anything that is going to be typically pleasurable tends to hit that pathway. Same thing with serotonin, not necessarily pleasurable, but that has a lot to do with emotion. It's also in your gut. So there are some general pathways, general patterns that you can look for when you're looking at these neurotransmitters. Why am I telling you this? The reason that I'm telling you this is that when we're talking about some of these drugs, these pharmacological agents, these toxins, these toxicants, all of them matter because they hit these receptors. And when they hit these receptors, they have effects, and those effects matter. So what we're going to be talking about today is a lot of these toxicokinetics, which are right here, and then we're going to be talking about, okay, once those go in, how are you actually getting your effects? So, for example, when you look at absorption, this is how chemicals gain access to the body, and without getting too deep into it, a lot of it has to do with how big of a molecule it is, and if it's soluble in water or if it's soluble in fat, so hydrophobic. But what I find is really fun, my favorite part, is more of the charge of the chemical. So if it's non-polar, it tends to access at least the brain a lot faster. So amphetamine gets absorbed pretty fast, and passes the blood-brain barrier. But if you add a methyl group to it, it becomes less polar, so more non-polar. It can enter the brain faster. When things enter the brain faster, they tend to be perceived as more pleasurable. So it's pretty interesting. Also, when things enter the brain faster, people tend to like that a little bit more. So for example, if you're looking at concentrations in the brain, this is unrelated, but still pretty similar. If you look at things in the brain, the sooner that it can get in the brain, that's typically what's perceived as more pleasurable. And the part that I find really interesting is when you look at the ingestion aspects of things, that starts talking about your distribution. So when you consume something, it typically has to go through the stomach and the intestines in order to be absorbed. So depending on the pH of the molecule we're talking about, it will either be absorbed in the stomach or the intestines or somewhere throughout the process. But when you ingest it, it has to goes through the liver to the via the portal vein through the liver, and it gets metabolized. And when that happens, some of it gets removed and taken away from that, what's called that first pass. So you have less of a concentration there to affect your receptors. And it also depends where your receptors are. So like we were talking about with serotonin, if you're in the gut, there's a lot of serotonin receptors in the gut. There's a lot of serotonin receptors in your brain. So there are some, you would imagine that if you have something that's going to hit the serotonin receptors, those might be some regions that are particularly susceptible, if you will. You also have metabolism. So once something gets into the body, one might think that you have, once it's metabolized, you would have less of it available to do its thing. And that can or cannot be true. So for example, with methanol, if you drink it, that's bad because when it gets metabolized, it actually produces formaldehyde. Formaldehyde can make you blind, so you don't want to do that. Like same thing with acetaminophen, so that's your Tylenol. And if you have too much Tylenol in your body and not enough glutathione to metabolize it, that can produce some toxic byproducts as well. So we typically think of metabolism as a good thing, but it's not always the case. Likewise, you have excretion. So typically the way things are excreted in the body depend on how it's coming in. So if you are breathing in gases, typically they're going to be excreted through the breath because it goes down through your lungs, back up and out. With metals, they typically are in the hair, so that's how we're going to be assessing that later. And then it depends on the solubility. So when you have fat-soluble things, it's harder to use urine to excrete that. So those things tend to stay in the body a little bit longer. And I always remember the fat-soluble vitamins and the warnings that they'll make with those, saying don't take too much of these because it's a lot harder to get rid of those. And then some things aren't excreted at all. So your nitrous oxide and your magic mushrooms are two examples of things that stay pretty much intact and can be consumed after being excreted through the body. So pretty gross, but it is effective. So this brings us into our dose response curves. And I found a really beautiful example through this site here. I'm going to pull it over, which is right here. And I love this because whenever you're talking about dose response curves, is you'll have some sort of concentration along the x-axis, and then what that effect is along the y. And so this could be, how many receptors is it binding to? But typically, when we're talking about environmental health, it'll be what are the effects that it's having. So you're going to have either this linear scale, and again, you can read right here of what it says or go to and play around with it yourself, but it allows you to look at either a log scale or a linear scale. And the part that they're talking about is this this concentration. And this is really important because when we start going into this helps us look at so this is the potency of something. So this is the maximal effect that you're going to have. And then some drugs are going to be more potent than others. So for example, a drug that's more potent, you can scroll up here and you can see that you need less of a dose to get the same effect. This is called the EC50. So at 50% of the effect, what is that dose? If you have less of a potent drug, so you might think of something that might be acetaminophen. We're going to be talking about that in a little bit. So something that's less potent, you need more of the drug in order to get the same effect. So again, very potent, not as potent. If you click on through, then you have this therapeutic index. And this is where things start getting, I really dig this, and here's why. All right, so when you're talking about efficacy, so say what our efficacy we're talking about is pain management, for example. So something that is really efficacious, morphine blocks pain every time, well, most of the time until you start getting too addicted. Anyway, different conversation altogether. But it's effective at blocking pain. When you have a drug, so acetaminophen, for example, it's less effective. And so here you go. So when you start dropping that, you have less of an effect at this EC50. Okay? And then finally, we're going to get to this therapeutic index. And all that says is at some point when you have your EC50, your effective dose, right, here's the desired effect that you want. At some point, you're going to have some toxic effects. So this could be, maybe you start sweating excessively, maybe you have hair loss. At some point, there's going to be a lethal dose, perhaps, where 50% of the population is going to die upon taking that drug. And the goal for the therapeutic index is simply to get this as far away as possible. So if you give a certain dose, so here's your dose down here, say this is 100 nanograms, and down here this is 1 nanogram. That might be a larger difference than 1 versus 1.5, for example. Making up numbers, but the general principle's there. So again, a little bit more dangerous, less dangerous. So they'll start doing this therapeutic index by calculating this EC50 for the adverse over the desired effect. So you'll see that a lot as we go through. All right, so look through that as you need to. And this is something that I showed in class that I think is really a nice example of this. So when we talk about some of these adverse effects, so here you have heroin and fentanyl. These are two drugs that hit the opiate system. This is showing the lethal dose of both drugs. And it's pretty obvious that fentanyl is way more potent because it takes less of the drug to get the same effect, in this case the lethal dose. And the reason that we bring up these curves is that when we talk about, say, heroin and fentanyl and some of these opiates, so here, this dashed line right here, this is overdose from stopping breathing. So you don't want to hit this. This is bad. Right here is this blue is powerful hospital pain relief, and down this yellow line, this is 1 Vicodin tablet. All right. So if you're taking fentanyl, you're heading up to this sleep apnea death thing pretty fast. It's pretty potent. Whereas with heroin, you can still hit this death thing, but it takes a little bit more drug. Conversely, here's your buprenorphine. This is an agonist at the opiate receptor. So it still hits these opiate receptors. It still gives you pain relief, but it's not at that dose that's going to kill you. And this is why it's used pretty often. This is the text directly from this graph. So just in case you want to read and compare, important. And then here's another graph showing the exact same thing, where you have these full agonists, so methadone, which was going to hit those receptors, buprenorphine, which is going to hit it, but partially, so you're not going to go all the way up. And then you have your antagonist, which basically blocks the receptor, knocks it out, so you don't have that effect whatsoever. Okay, so the reason that I'm bringing all of these things up and why it matters and how people are taking things is that the chemistry and the toxins that we're going to be talking about, or the toxicants, it's going to matter about how they're being taken into the body. So for example, if you look at this organophosphate, it's way more potent in terms of, way more toxic rather, when you take it orally than if you rub it on your skin. So the reason, or the way that organophosphates work, is that they work at the acetylcholine receptor. So typically what happens is, so this green box is a normal acetylcholine, where it will be released from the cell, it will bind to these receptors, and you'll get an effect. Everything's great. Acetylcholinesterase is what stops it. It will bind to the acetylcholine in this and say, all right, everyone out of the pool, party's over, all right, pull everything out, and it stops the signal. You don't want the signal to continue, because the problem with it, and this is what happens with organophosphates, they block the acetylcholinesterase. And why that matters is that now you have all of the acetylcholine and the nicotinic receptors and the muscarinic receptors having this field day of a party. But that's not necessarily a good thing, because that constant activity, you have these effects down here. So ultimately what's going to kill you is that your diaphragm stops working. You're not breathing anymore, and you die. You have, of course, these various toxic effects along the way, so the dose really matters. But that's no good. So often what they'll do is they will give atropine, which is down here. So that is a muscarinic antagonist. It's just kind of, hey, chill out. We're not going to have the muscarinic receptors being activated as much. So it's just a way of kind of trying to balance things that are being released to activate the receptors and shutting things down again. Now, when we're talking about these things, I'm not expecting anyone to know necessarily the mechanism, but what I'm looking for is, I want you to understand the general patterns. So when you have something that's going to hit a certain pathway, you're going to be able to predict effects based on that pathway that's getting hit. So, and it also doesn't have to be just poisons. So for example, we talked about BPA a little bit. And so you have your estrogens, you have BPA. BPA is one thing that's in plastic, but it doesn't have to be something that's man-made. You have a ton of different plant products. These are pollutants, pharmaceuticals, fungal products, all of which are very similar and act in an agonistic way on the estrogen receptor. fortunately, so the National Institute of Environmental Health Institute, so NIEHS, National Institute of Environmental Health Sciences, so that they have the National Toxicology Program, and what they do is they look at the effects of these different chemicals on the body, and they will rate it accordingly. So it's a nice way of finding out what's working, what's not working. When I say working, I mean what's toxic and what's not toxic. What do we need to worry about? Where do we need to worry about? Who's most at risk? And then ultimately it comes back to dose makes the poison. So if we're having very, very small amounts versus very, very large amounts, and the amount of time, all of those things are going to matter, but it really makes a difference. So we have one of our first science educators right here who used to give talks to the public way long ago. So it all comes back to science education. So tell your friends, science is fun, and I'll see you in class. Bye.